Yeah, I'm going to talk to you today about USVs. And USVs, if you don't know, stands for Uncrewed Surface Vehicles. And I can tell you a little bit about our company, where we've come from, some of the trends in the USV market, and some of the software which does use AI, as well as normal autonomy within it to make these effectively robotic ships. So we're a daughter company of Submergence Group, which is a company in America. Really, there's an opco for delivering submarines. We've been designing and building submarines for the US and the Royal Navies for about 15 years, mostly in high states of automation and, latterly, encompassing software involving AI. We're the crazy guys who sent the Mayflower autonomous ship across the Atlantic in 2022. So that was a tech demonstrator for both our engineering capability and our software capability. She successfully navigated with no one on board from Plymouth, UK to Plymouth, Massachusetts in May 2022. We had a little pit stop in the Azores when we had a mechanical problem, and a little pit stop in Halifax for another mechanical problem. And that is really, in brief here, it's not the software which is limiting the application of these drones, if you like. It's the engineering and making sure that the everyday engineering for simple parts, a $20 part, isn't your failure point. So, part of the same companies, we won the contract to do the Royal Navy's new autonomous submarine, 12-meter submarine. We're working with the US Navy. This is a little company in Plymouth, by the way, 80 people at M-Subs, 30 people at Marine AI. We're not talking Thales or British Aerospace. We won the contract for the US Navy to deliver their executive autonomy for their new 50-meter unmanned frigate. And we are probably 2/3 of the way down the track of actually delivering that. That boat's on the water, floating and operating next year. So all of that leads us to the fact that we thought, well, maybe what we should do is offer our own turnkey autonomous package so that industry can just take that and use it, whether you're a hydrographer, surveyor, border force. The uses are really endless. But if we can offer a vessel which is completely autonomous with all the software, with a remote operating center to oversee it, so you just come to us and say, I want that boat, I want to charter it, I've got a job for it for 3 months, that will solve some of the problems. So this is Zero USV. We launched it in March this year. We've received very good press so far. There's been a lot of interest. That was unfortunately me in the mugshot there. Where are we? So the key thing for us, the business model for us, is that this is a charter model. We're not building these to sell. We're building these to charter out to people. And that way we're able to offer the support which is necessary and not get bogged down in doing the training which might be necessary to be able to use the vessel successfully. We're calling them Oceanus, and that is because that's the first child who's born after Mayflower, on the Mayflower ship which sailed across the Atlantic. So as I say, we monitor the boats 24/7 in a remote operating center. Even though they're being operated autonomously, there's not a drone with someone piloting it. And we set up a network so that we have a hub in Australia, a hub in Canada, a hub here in the UK, so that we can offer a global network for these vessels. Here's just some of the CAD design shots. I'll come on to in a second. You'll see there's an aluminium build, but the principles are that this is a vessel which is capable of over-horizon missions. There are obviously other autonomous vessels out there at the moment. Generally, they are only capable of doing near-shore operation. They're all fully remote controlled or near a mothership. You can't just dispatch them from Plymouth and say, okay, here's your mission. We'll see you in 3 weeks' time. Off you go. That's what this does. So it's able to do the functions of a fully autonomous vessel, but with no one on board. And as I say, we don't care what the job is. It can be hydrographic survey, it can be bathymetry, whatever you want to do. We don't mind. Just some nice fancy renders of the boat. You can read this as well. We've got the first 2 boats which are currently in build in Weymouth, and they're at the painting stage. So we've built the hull. I'll show you some slides and a little bit of video in a minute. And we've just begun the fit out. We're planning to have them on the water in the next 6 weeks. So then we'll do the factory acceptance tests, and the first boat actually going to Australia in November. We've ordered boats 3 and 4, and as I say, by end of next year, we're planning to have a fleet of between 8 and 10 boats on the water available for charter. So yeah, just a little bit about how the boats are built for those who are interested in that side of things. The hull arrives with a flat pack, laser cut, stainless steel self-jigging kit. What does that mean? That means it's like a pile of Lego which slots together. Everything's all cut and pre-formed, and so you can actually assemble the hull really very quickly. This is a little time. This is going to work. I've got a little time lapse here. How do you do that here? Maybe struggle. No? Oh well. That was going to be a little time lapse. I'm going to press the space bar on the computer. Maybe can you press that maybe? No? Okay. If you just press the space bar, hopefully okay, don't worry. Anyway, the boat's painted, as you can see there now, and we're shortly starting fit out, which involves putting in the generators and the electric drive. I'll skip over this because I appreciate it's the end of the day, but this is a diesel electric vessel. So it's got an electric drive with lithium batteries and generator backup. We're not able yet to offer a fully electric vessel with long distance range. You just couldn't get enough batteries in the vessel to be able to do the distance. I mean, you must have seen all the press about range anxiety for cars. Well, you can, multiply that by many factors at sea. And really, what we can do here by having an electric hybrid drive and making a very efficient, very quiet, operable vehicle, which means that when we're doing survey work, we can run it in quiet mode, i.e. electric, and get very good quality data. When it's sprinting and going out to the survey grounds, you're using diesel electric, so the generators are running and they're powering the electric drive. Just cover some of the AI type stuff. So there's no one on board. So we're very heavy on sensors so that we can pick up all the necessary information we need. And there's just some of the things we use. We're NVIDIA GPU based, but then we're using regular things like cameras, radars, AIS, GPS, weather stations, thermal cameras to gather all that data information together and then do some data fusion. So yeah, as I say, the boat is acoustically quiet. The cruising speed is 7 knots, which might not seem very fast to you, those who aren't mariners, but is a pretty good cruising speed. She'll sprint at 12 knots, and we could do survey work at 3 to 4 knots. So we can run off HVO. So we're about as green as we can make this vessel. The hull's fully recyclable. We're using electric drive. We're minimizing the CO2 output. One of the challenges with running USVs offshore is the redundancy, and you've got to balance the redundancy against commercial viability. But we struck a balance, and effectively we have a port and starboard, a left and right system. Either one of those systems can run the whole vessel. So you can swap from left to right and still run the whole vessel. And that basically gives you 100% redundancy. The main thing here, as I say, we're just trying to reach out to as many markets as possible. I mean, we've had inquiries from border force who potentially want to, not just UK, I'm talking about worldwide. We've had border force who potentially want to have half a dozen of these, stick them off the coast of their country, use them effectively as drones, which they can go out and cover a wide area, and then feed data and information back to land-based stations on what's going on. Potentially carrying life rafts, which can be deployed automatically, autonomously, if people need assistance. So the payload base is like to be agnostic. You can put anything you like in there. And this is not a yacht. This is a motor vessel. The keel's there really as a strut to carry sensors, so we can put on different types of sonar gear and allow it to pick up data. So just very briefly, we use AI-based software on the boat. Our software is called Guardian. That's the software which the US Navy are using, the UK Navy are using on their vessel in our software stack. And this is really quite a sophisticated blend of different technologies. Let me get to just. So, yeah, it's there. Let's get to the next. So, the key thing is that we're not a black box. We're not just a box in the bottom, which no one understands. We use is completely a stackable system. We can add in and take away any part of it without it disrupting it. So we can customize it to a customer's needs and make it as sophisticated or as simple as possible. And so really, in the world which we're operating in, computer vision forms one of the key building blocks to the whole AI system. And that's where you start. And then you blend in different sensors on top of that to give you more sophistication and more reliable information and data on what you're doing. And this is what this slide shows here. Hot warm redundancy patterns, that just means, again, we're running a port and starboard or left and right computer system. So if one fails, we can switch over to the other side without any loss of any loss of control. For those of you more technically minded, we're using Marlin protocol, which, if you know anything about that, means it is quite easy to understand. It's written in real language, rather than in code. It's also encrypted, which is pretty helpful. So what we're doing, and you'll see some examples coming up in a second, is we're taking the data we're getting from the various sensors, fusing that data, and then using effectively probability to score whether a target is of concern or not. So in simple terms, you can visualize yourself standing on the bridge of a ship. Your eyes are out there looking at what's going on, and you might see 4 or 5 different ships. You'll then maybe look at your radar, and you'll see maybe 8 or 9 ships. You'll then maybe look at the AIS, which is giving out position and tracking information, and you might see 12. You look at your GPS for where you are, and then you in your mind will blend all that, fuse all that data together, and make a decision about what you think your ship should be doing. Well, we're doing the same thing. We're just doing it mathematically with the compute power. And we call that contact data fusion. I mean, you must have seen, if you're involved in this sort of stuff, or have seen this sort of stuff before. Computer vision, basically, you label and identify a target. On the right-hand side, that's actually so that we're zoning an area of interest. We're not interested in what's happening in the sky. We're only interested in what's happening on the sea. So, for instance, about 4 years ago, we got asked to do a project where we went down the Thames, picking up targets, and the previous people who'd been to see us had had a problem because all they could do is pick up buses on the bridges going across. So it's being able to have that level of complexity, which says, okay, we're only interested in stuff in this zone, and that is all we're going to deal with. That's again meant to be. I think it's very exciting. So move on to. So radar, we use two radars. We use a standard X-band radar, which is what you might find on your normal commercial vessel or ship, and has the standard sort of range up to about 30 miles, and will pick up targets for us and go into that contact data fusion model I was talking about. We also use a very sophisticated W-band radar, which is like a high-definition radar. It's got a fairly low range, only up to about 1 kilometre, but it will pick up things as small as a bleach bottle on the water at 1,000 metres. And it's normally at this point of people who are involved in this field, so why are you using LiDAR? That's because LiDAR and water don't go together very well. And so you're much better off with radar. It can work in any conditions in terms of rain, sea state, etc., etc. Plus, even on a really good LiDAR, you're looking at probably max 200 meters range. Whereas, as I say, on this W-band radar, we're getting 1 kilometer. So this is where the AI bit's going on in the tactical guidance, the tactical engine. You know, we set it a mission. We're taking in all the data I was talking about from the contact data fusion, and then in the clever bit, the dynamic path planner is working out what to do. I'm hoping we can get these videos to run in a second, because they will show you some of the So on the left-hand side here, the far left-hand corner is us. It's a white vessel with a stand-on vessel. And we've got a scenario where there's 3 other vessels coming towards us, and we've got to understand how to get out of that without hitting each other. So this shows how the software looks at the situation, is able to resolve what is the best course of action, and then have an outcome which is both safe and allows the vessel to carry on without a collision. All right, let's work here. You still come back to it. Okay. So this is another example. Okay, doesn't like the clicker. Could you just try pressing the space bar when we go back to it and see if it all plays? No? Okay. Let's go back to that a second. And so when this runs, what this shows is how it's actually taking in bathymetry data, so depth data, chart data, and using, oh, there we are. This is speeded up, by the way. So you've got the yellow vessel coming out, the white vessel coming in, and it needs to avoid that vessel. Plus, it needs to take in consideration the depths, which may be, significant for that particular vessel. We're pretty lucky. Where we operate and test in Plymouth is one of the few areas in the world, actually, where they have something called S100 data, which is where the whole charted area has been surveyed specifically digitally, down to 1 centimeter accuracy, and the data we're using is actually digital from the outset, whereas 99.9% of all other charts are actually raster charts which have been digitized. So they were effectively human-drawn charts which have been made digital, and then you're picking them up with all the errors which they encounter. So just on the USV market, I mean, it's a massive, we see it as a massive growth area, which is why we're going full bore into it. I mean, you must have read all the stuff about the wind farms. You know, before you can build a wind farm, what do you need to do? You have to go, before you can get a license to build a wind farm, you have to go and survey it, survey the area, provide the feedback to that. Now, if you're on a crewed vessel, first of all, they're very expensive, and it takes a fair amount of time. Using the technology we're proposing here, you can have multiple USVs operating together. So when you survey, you're effectively going up and down in a pattern. If you end up with 10 or 12 of these USVs all operating together, you increase or decrease the amount of time it was going to take by the same order of magnitude. So it's very significant. And the push through the wind farm, to put it in some sort of context, I was at a conference the other day, and if we were able to put up one 20 gigawatt turbine every day between now and the end of the decade, we still would not meet the target which the government has set. That doesn't take into account the fact that we never built a 20 megawatt turbine. The biggest we've ever built is 14. And the fact that no way in hell we're going to build one every day. So we need this technology, and we need it now to get out there to accelerate what's happening so that we can meet these targets and get some more green electricity. And that is just one small application. I've touched on some of the other areas. I mean, when you stop and think about it, there's a huge amount of areas for autonomy, for autonomous ships. And why? First of all, they're cost effective. There's no crew on board. Yes, you may have some people ashore watching what's going on. That's nothing like the cost of running them with people on board at sea. And they don't care whether they're out in, a force 10 storm, or whether it's December, whether it's Christmas Day, whether it's up in the Arctic. They don't mind. So it does open up huge areas for these vessels to operate. Now, the communication needs are obviously particularly pertinent to here. These aren't being remote controlled, so you don't need to have data always on. However, one of the very significant needs in this day and age is people want to have the data back off the vessels as quickly as possible so it can be processed ashore and got to the client as quickly as possible. So that is a very, very real need, and having good satellite comms for that is essential for the industry. So, I mean, as I say, for the vessels, we can operate them. They're designed to operate without any satellite comms because for safety reasons. And these are just some of the applications. I mean, we have touched on environmental monitoring. That's another huge section. We touched on the offshore wind, the oil and gas side. We touched on border security. And we touched on hydrographic survey work. And we talked about doing pre-survey work for things like offshore wind farms. And there's a whole defence piece, which is there as well. This is a little 3D render. Happened to be in the Dazzle format for defence. This is some Apex floats, which we actually, when we sent Mayflower across the Atlantic in 2022, we had 4 of those on board, and we deployed those remotely with obviously no one on board, and they're used to measure what's called the thermoclines, which is the different layers of temperature in the Atlantic, which is very particularly important for defense applications for submarines. If you can hide in a thermocline basically in a submarine and not know it's there. But these are dropped into the ocean, and the fact that you can do that autonomously, remotely, is a game changer, really. Bit of pretty sonar stuff. And that's what the boat looks like. And that is pretty much it, I think. So there we go. Hopefully you've learned a little bit about USVs and where we're going in the industry. Thank you very much.
Thank you. Any questions? Sorry about that. I see these said that they knew something like the guys to Satan.
No, not for safe reasons. Well, from the point of view that we don't want to be reliant on a satellite communication for controlling the vessel. That's it. If you have a loss of comms and you're reliant on being able to control that vessel, then that is obviously an issue. So the software is designed to be able to use its AI, use its sensors to be able to navigate safely. The key thing is being able to have that the satellite connection to be able to transfer the data and get the data back. That is absolutely key. So it's not like we don't need satellite communications. We very much do need them, especially for all these jobs and situations I've been talking about here today. We don't need it to drive the vessel, but that was a deliberate sort of safety case, as it were, because otherwise, if you've got no comms, then you have to get a situation where the boat defaults are stopping. So you've got all these boats bobbing around, they lose comms for 10 minutes, and your all systems stop, which is not good either. Well, we've been using, when we did Mayflower, Leo wasn't really advanced enough. So we're using an Iridium system then, so which is obviously ultimately low bandwidth, which is why we're able to refine our software to be able to be used in a low bandwidth environment. These days we'll end up using Leo. I mean, we use Starlink, and and if we have to fit two, we fit two. I mean, it's such a bonus to be able to have that available, bluntly. But we will fit an Iridium system as a backup, because we do again need to have the reliability of having a comms channel open of some form, just to monitor the boat and look at the data. Yeah, I mean, we're not surveyors as such. I mean, we are literally there to provide the vessel, and we are pretty agnostic as to what people use it for. I mean, I think when as you say, there's so many different applications, and cable laying is certainly one of them. Surveying the cables, surveying the wind farms will be the gift which keeps on giving, really, because I touched on surveying before. You then have to survey once the wind farm turbine's up, and then again every year. So, and they're just getting bigger and bigger and more complicated. So, yeah, no problem.
Good. Good. Steve? Maintain artificial intelligence on the best, the processing with best of being out.
We do the model which is deployed on the vessel is using AI on the vessel. What we're not doing, though, is retraining models on the edge. That's a step too far, really. Because the amount of power needed to train the models, is our server in the cabinet at the back of the office is very power hungry and huge. But yeah, we're certainly using AI on the edge. We're using little NVIDIA. The change in the market really is NVIDIA bringing out their small GPU units and being able to use those in situ. Absolutely. Correct. Yeah, we only have to send back what we're missing. Yeah, you got it. Any more?
I think we're good.
Thank you very much indeed.
Much, yeah.